What is going on, guys? Okay, so today we're going to be making something pretty badass. This is a 150,000 volt stun gun and it's completely homemade. Let's get started.
Okay, so the first thing that probably came to mind is this thing legal? Well, lucky for me, in France, handheld stun guns are considered Class D and are therefore perfectly legal to own.
However, a device capable of delivering an electric shock from a distance, such as a taser, are Class B and are therefore not available for the public. So, as long as this thing doesn't shoot out, two prongs, I shouldn't get into too much trouble, hopefully.
Alright, so let's talk about how these things actually work. So, there are a few different types of voltage multipliers, but I will only talk about the one I plan on using for my homemade stun gun, or this video will be 5 days long. These are the internals of a stun gun I picked up at my local self-defense store. In this particular style of stun gun, you'll find 4 main parts. This is the power source, which in this case is a 9-volt battery. This is the first stage pulse transformer, so this bumps up the 9 volts from the battery to around 3 kilovolts. This is the main pulse capacitor. This stores the energy delivered by the transformer and instantly releases it in one powerful pulse once it charges up to a certain voltage. In this particular stun gun, this happens around 20 times a second. Finally, this is the second stage trigger transformer that takes those 3 kilovolt pulses from the capacitor and bumps them up to around 40 to 50 kilovolt. And, of course, there's definitely a lot more to it than that, but we'll be taking a look in more detail later in the video. The first piece of the puzzle I wanted to tackle is the oscillator circuit. This may sound easy enough to generate with a 555 timer, but I wanted to understand what frequency, what amplitude, what pulse width, etc. would be optimal. So I set up this little test bench. Here I have a function generator board capable of generating a square wave up to a frequency of 300 MHz. This board also has a pulse width modulation potentiometer, which allows me to adjust the duty cycle of the square wave, which is extremely handy. The board is being controlled by an Arduino Nano. I created a very simple code that allowed me to control the output frequency by adjusting this potentiometer. This LCD display simply lets me know what frequency is being generated. And of course, because this board can't supply nearly enough power to directly drive the primary coil of the transformer, we're going to need some sort of transistor. Here I chose a beefy MOSFET. So to make things simple, these will basically take a low voltage signal and allow huge amounts of current to flow through. Kind of like a switch capable of switching on and off extremely fast. I won't go into too much detail here, but beefy MOSFETs like these do require massive gate currents at high frequencies due to the parasitic capacitances. That's why I'm driving it with this classic push-pull transistor setup. But basically, low power signal in, high power signal out. Great! So all I need to do now is to find a high voltage step-up transformer. Whoops. So it turns out that this type of transformer with a secondary voltage of at least 3 kilovolt is pretty much impossible to find. Luckily, I was able to find these transformer winding kits. That way I could wind my own coils and get the output voltage I wanted. Perfect! And here's what came in the mail. So here I have what's called the transformer pot and the ferrite core. Alright, time for some quick theory. So the way a transformer works is fairly straightforward. You have a primary coil and a secondary coil. A ferrite core runs through these two coils. When an alternating current is run through the primary coil, according to Faraday's law, a magnetic flux is induced and conducted through the ferrite core towards the secondary coil. This in turn, when under load, induces a current through the coil, and a voltage can then be measured across the secondary coil. The most important formula to understand is as follows. Its output to input voltage ratio is proportional to its secondary to primary winding number of turns. For instance, if we have, let's say, a transformer with 10 primary windings and 1,000 secondary windings, and apply 5 volts across the primary coil, we should, in theory, get 500 volts on the secondary. Now, all these formulas are true if the input signal is a pure sine wave. Here we don't have a sine wave, but like we saw before, a square wave. We could generate a high power sine wave using a power amplifier, but the thing is, these transformers can definitely be driven with a square signal.
However, accurately calculating the current flow, the ideal number of turns, the input voltage, etc. would have been a nightmare. This is why I decided to set up this test bench in order to experiment and try and figure it out through trial and error.
Okay, so let's get winding. Because I had absolutely no idea where to start, I just rolled around 1,000 turns of thin insulated copper wire for the secondary and 10 turns of thicker wire for the primary. However, before I even had the chance to experiment with anything, I noticed some major internal arcing. This is due to the fact that the thin insulation on these copper wires instantly breaks down under the high voltages, and once an arc is formed, the entire transformer becomes useless.
This means I needed to figure out a way to better insulate the windings.
A common method I found online was to wind an entire row, making sure the wires don't overlap. Then I could insulate that row using a thick layer of tape or plastic. Then I could simply repeat that whole process until the desired number of windings is achieved. But yeah, so perhaps I was doing something wrong, or the voltages I was getting on the secondary were simply way too high, but I simply kept getting internal arcing, and I was starting to get a little bit frustrated. But after extensively digging around on the internet, I finally came across these super cheap high voltage transformers. I got a few different types of transformers, but in the end, I decided that the first one I bought was perfect for this particular project. I bought a few of these kits that came with the same transformer and an oscillation circuit. However, yeah, definitely not that great.
So how does a pulse transformer work? Well, they rely on a very interesting phenomenon that occurs when you apply a current through an inductor and then suddenly open the circuit.
As the magnetic field collapses, a massive voltage spike is induced on the coil, easily hundreds of volts on the primary. This voltage spike is the principal car ignition coils use. Notice that the spark only occurs when I disconnect the primary. So here it's easy to see that in theory, the more average power we want to be transferred through to the secondary, the faster the connecting and disconnecting needs to be. In fact, this needs to happen tens of thousands of times a second, and that's why these pulse transformers operate at such high frequencies. Here I'm ramping up the frequency all the way up to 1 kHz. So after some experimenting, I found that only 3 to 4 turns on the primary seemed to give the best results. I wound 4 of these wires in parallel. This basically behaves like a bigger wire, which results in much better power handling. It's even recommended to have multiple strands of smaller wire instead of one big one due to power losses caused by the skin effect. I poured the transformer in epoxy resin to help with the insulation. This is a common method to insulate high voltage circuits and to limit losses due to corona discharge. To get rid of any air bubbles trapped inside the transformer, I had to pull a vacuum on it for a few hours. And I was finally able to get some decent arcs on the secondary. However, I started to realize that I was definitely going to have an overheating issue. You see, with a positive square wave, there will always be a DC component which will result in power being converted into heat. Also, the MOSFET was switching hundreds of amps, which meant that I had to mount it on a heatsink to prevent it from overheating. And of course, a setup this large could never be mounted in a handheld device, so I had to come up with another way. And then I remembered something. If I simply hook up a capacitor in parallel with the primary inductor, I could then get a resonant circuit, similar to how Tesla coils work. A capacitor hooked up to an inductor will pour charges back and forth into each other at a frequency given by this equation. If I excite the circuit by feeding a square wave signal into it at that resonant frequency, we can get massive voltages and therefore massive currents running through the primary. And not only that, but the current running through the primary is a sine wave, and this results in an almost non-existing DC component running through the coil, which results in much better power handling.
Now, for a stun gun to be effective, high voltage is necessary so that the delivered energy is capable of arcing through clothing, and the high voltage is also used to overcome the resistance of the human body.
The important thing to understand is that the strength of a pulse depends on the voltage, the current, and a third very important variable, time. A unit that encompasses these 3 variables is energy, measured in joules. If we take a look at the datasheet for the M26 police taser, for every pulse we get a whopping peak-to-peak current spike of 23 amps with 8,000 volts across the probes. The peak output power there is almost 200 kilowatts. Now that is a stupid amount of power, but if you look at the graph, you will see that this whole event actually only lasts 50 microseconds. And yeah, if it were continuous, the attacker would probably just explode.
So to recap, stun guns deliver high voltage and high amperage but very low energy pulses. And the perfect component to deliver these 3 things is, of course, a capacitor.
Great! Now I can actually start designing the rest of the stun gun. A capacitor needs direct current, or DC. However, at the output of the transformer, like we saw, we have an alternating current, or AC.
So this basically means we need to rectify the output current. And to do this, we're going to use a puny single diode rectifier, as this will be more than enough. And basically the way these work is... Sorry. Hello?
Nick, what the f*** did you just say?
I'm sorry, who is this?
A puny single diode rectifier is enough? Really?
I mean, is it not?
No! A single diode rectifier is weak! You better not use them in high power applications. I mean, shouldn't you know all this stuff already? What are you, a mechanical engineer?
No, I dropped out.
You need a full bridge rectifier. Full bridge! I have an eye on you.
Alright then, so I guess we'll be using a full bridge rectifier. A full bridge rectifier consists of 4 diodes in this arrangement, and a diode allows current to flow through it in one direction but not in the other. With a single diode rectifier, when an AC signal is applied to the input of the rectifier during the positive duration of the cycle, nothing changes on the output. However, during the negative part of the cycle, the rectifier simply blocks current flow. Now, with a full bridge rectifier, during the negative duration of the cycle, the rectifier flips the signal so that the output voltage never drops below 0. So, the first part of the circuit can be traced like so. Cool. Here we can add our secondary transformer with, just like the first one, a few turns on the primary and a lot more on the secondary. Now, if we were to connect the primary of the second transformer in series with the secondary of the first coil, this coil would simply act like a short circuit, and the capacitor would never be able to charge up. And of course there would be absolutely no output on the secondary. This is why we need some sort of switch that would be open while the capacitor charges. Once the capacitor reaches a certain charge, therefore a certain voltage, the switch would close, allowing massive amounts of current to be instantly flowed through the primary, creating a high voltage pulse on the secondary. You'll notice that when the switch is closed, we have an inductor and a capacitor in parallel, just like before. This means that they will, again, pour charges into each other and oscillate at a certain frequency. And if we take a look at that pulse graph from the X26 taser, that is exactly what we see here.
Anyway, the easiest way to create a high voltage switch is to simply have 2 conductors separated by an air gap. And that's it.
And here's how they work. Every material has a dielectric strength measured in megavolts per meter. For instance, air has a dielectric strength of 1.5 to 3 megavolts per meter. That means that if we had 2 probes separated by 1 meter, we would need to apply 1.5 to 3 million volts for the insulation air provides to break down, ionize, and form an arc. This also means that if we wanted a switch that closed between 1.5 and 3 kilovolt, we could simply have 2 pieces of metal separated by 1 millimeter. And voila, we just created what's commonly known as a spark gap.
And guess what? We're done. That's it. Well, in theory. Let's order the high voltage capacitors and high voltage diodes and see what we can do.
And here they are. So after a little bit of soldering, here's what that looks like. So for the first test, I used a piece of wire to temporarily simulate the trigger transformer. I pumped 10 kHz at 2% duty cycle through the primary, and to my surprise, it seemed to work flawlessly. However, after listening to it for a while, I noticed something pretty annoying. The pulses seemed to happen at very random intervals. And to try and figure out why, I used a cheap $30 oscilloscope. This particular oscilloscope can only measure up to 50 volts, which is no good. To get a decent voltage measure, I'll be using an improvised 100-to-1 voltage divider. And yeah, this setup is definitely pretty dodgy and not very accurate, so I definitely wouldn't use this on a more expensive oscilloscope, which is why these cheap ones are so awesome. Right, so let's measure the voltage across the capacitor. And as you can see, the capacitor slowly charges up and instantly discharges. So that's exactly what we expect. However, you can see that the discharge voltage is indeed very imprecise. So why is this? Well, we saw earlier that the dielectric strength of air can vary between 1.5 and 3 kilovolt per millimeter, not a fixed value, so the air isn't the best material for this.
So, if only we could have some kind of spark gap encapsulated in a gas with a very precise dielectric strength. Oh wait, what's this behind your ear? A surge arrestor gas discharge tube? Pfft, perfect!
These discharge tubes are usually used for high voltage circuit protection and should work flawlessly for our purpose. Okay, so let's replace the spark gap with the discharge tube and see what it does. Nice, much more precise, and the pulses are nice and evenly spaced out. Now let's move on to the dreaded high voltage trigger transformer. I wanted the output arc to be about 50 millimeters long. That means the transformer needs to have a peak output voltage of around 150 kilovolts. Probably a lot less than that, but this will make sure it's able to arc across that distance every single time. To maximize efficiency, we'll be using a ferrite core. I ordered a few of these ferrite rods used for crystal radios. I wound 10 turns of thick copper wire around it. Then I wound the necessary number of turns of much thinner copper wire around a piece of PVC pipe. The pipe will insulate the 2 coils, and once again, to my surprise, it worked flawlessly. But obviously, the issue here is that it isn't exactly compact. But before